Hello! Last time we looked at acceleration, and today we're going to look at how to graph acceleration. So last time when we looked at acceleration, we noted that acceleration is a change in an object's velocity over time. We measure this by finding the change in an object's velocity, dividing that by the time it took for that object to change its velocity, and measure the resulting acceleration in meters per second squared. There are two ways to graph acceleration, as a measure of changing position over time, or as changing velocity over time, which we see more often. So we're going to look at the less often example first, as changing position over time. To review, if an object's velocity is constant, that means that its position is changing in a constant way over time. So this means that over time, the displacement of this object will also be constant. So if you have a constant velocity, you have a constant displacement. This might look like this position versus time graph, where we see that an object's position is changing at a constant rate over the course of a certain amount of time. If an object's velocity is not constant, though, that means that it must be changing. And we call this change in velocity over time acceleration. And if the velocity is not constant, then its displacement, or its change in position over time, must also be changing. This means that the rate of an object's change in position versus time is not constant, so we wouldn't see a straight line. Let's go back to our dot diagrams to illustrate this point. If an object is speeding up, that object should displace more ground between seconds 1 and 2, and even more ground between seconds 2 and 3, 3 and 4, 4 and 5, and so on. Likewise, if an object is slowing down, we should see it start to displace less distance as this object decelerates. Because of this, because the displacement is not constant, in a position versus time graph, we would see something like this, where we would see a curve. That's because the velocity is constantly changing over time. So where does this curve come from? Let's take a look at an example. Here's our first example. A westward moving bicycle increases its velocity from 2 meters per second to 12 meters per second in 4 seconds. What is the magnitude and direction of the acceleration? Using our acceleration equation, which is the final velocity minus the initial velocity divided by how much time it took to change velocities, we can plug in some values. We know that our final velocity is 12 meters per second, and our initial velocity was 2 meters per second. If we do this math, that gives us a change in velocity of 10 meters per second. We then divide 10 meters per second by the amount of time it took this bicycle to change speed or change velocity. And in this case, that was 4 seconds. And if we do this math, if we take 10 meters per second divided by 4 seconds, that gives us a final acceleration of 2.5 meters per second squared to the west. And it's to the west because the bike was already moving in that direction, and it's increasing velocity, which means that the acceleration must be in the direction that the bicycle is moving. So what does this answer really tell us? It tells us that for every second this bicycle is traveling, it's covering 2.5 meters more in a second than it did in the previous second. Before we graph this, let's see that visually by putting some values in a table. At time equals 0, we know that the car is displacing 2.5 meters west. So that means that it is now 2.5 meters further down the road than it was before. But this bike is accelerating at 2.5 meters per second, which means that from time 0 to time 1, this bike is actually displacing another 2.5 meters further than it did before. So we have to add an additional 2.5 meters to this initial position to give us how much this bike is now displacing, which in this case is now 5 meters. Which means that at time equals 1 second, the bike is now 7.5 meters down the road. So at time equals 2 seconds, that must mean that the bike is now moving an additional 2.5 meters down the road than it was before, which means that we need to take the displacement that it had before, 5 meters, add another 2.5 meters to that. And that tells us that at time equals 2, this bike is now displacing 7.5 meters, which puts it at 15 meters at time equals 2. We could keep going, but if we continue to do this, we see that for every second, this bike is displacing 2.5 meters more than it did in the previous second. In other words, as this bike accelerates, it's increasing the amount of distance that it can displace every second because the velocity is changing. So let's put all of this in a graph. If we plot all these points on a graph of position over time, like this, and then connect them, we see that the change in the bike's position is not constant over time. It's curved. We see that the change in the bike's position is changing over time, which is what produces a curve. We also note that it's moving in the positive direction, since the direction of the curve is moving in the positive direction. If this curve was flattening out, say, versus getting bigger, if it was flattening out, that would tell us that the position or the amount of displacement would be decreasing over time. It wouldn't be covering as much distance, which would tell us that this object would be slowing down. And a quick note, this could also happen in the negative direction or in the negative axis. So if suddenly you see a graph where all of this is happening below this line, all of the same principles apply. If it's traveling away or increasing its position over time, it would still be accelerating, just in the negative direction. And if it was getting flatter, but on the opposite side of this line, it would be slowing down.